My name is Charlotte Spears, and this is my AP Calculus capstone project, and I will be talking about fractals. So in order to understand fractals on a more complex level, one must understand fractals on a basic level first. So the most fundamental and basic fractal is the Koch fractal, which is actually a Koch snowflake, and it starts off with an equilateral triangle like this, and then each line segment is divided into thirds. An equilateral triangle is created off these line segments. This process is done over and over again on every. This is an example of a fractal. And a fractal is a geometric shape or a set of complex numbers that are self-similar, and at any scale, zoomed in, enlarged, it looks the same. And so an interesting thing about fractals on a basic level is that there is a finite area. To help describe this, if I were to draw a circle around this fractal, we know for a fact that even if we reiterated this fractal to even the atomic level, it will never reach outside of this circle. The area is finite. However, the interesting is, and this area can be calculated by this, showing that it will eventually approach a constant. However, the interesting thing about the behavior of fractals is that while the area is finite, the perimeter is actually infinite. And this can be described by this. Let's say this side, from this point to this point, is placed here. S for side length. So just like this, if we were to divide this into 3 segments and create this, we can see that this side length is equivalent to 4 thirds of this. So this is 1/3, 1/3, 4 thirds. So with this idea, however many times you reiterate it, the limit as a number of iterations approaches infinity, perimeter the original side times 4/3 to the nth power will also approach infinity. Gotta go faster. Okay, so the easier way to understand this is if we were to have a circle with an area and a perimeter. But if I were to alter this perimeter slightly and make it slightly more rougher, arbitrarily I can say that this area is the same, but because I've made these sort of ridges and valleys, the perimeter is now greater. And if I were to do this, make these ridges and valleys more and more sharp, and make them infinitely more, the area is now still the same, but the perimeter is greater once again. And this can be stretched out to infinity, proving that the area remains constant, but the perimeter approaches infinity. So now, and here's another example of a fractal, one that can be applied to real life. Like a tree branch. This can go out, then it creates a pattern, and then again and again. Okay. So complex fractals. Complex fractals are merely fractals plotted on a complex plane. Complex plane has a y-axis that is an imaginary number and an x-axis that is real numbers. Therefore, an arbitrary point, say here, would be equivalent to a plus bi. The most common complex fractal is the Mandlebrot set. The Mandlebrot set uses the function f c of z equals z squared plus c, where c is a constant and z is the recursive solution to the equation. So let's say So this applies to the Mandlebrot set, saying that the values inside of here, when placed into this recursive function, will never exceed the number 2. However, these values out here that are shaded in blue symbolize the values that will go to infinity. So for an example, when c is equal to 1, the Mandlebrot set reiterates like this, starting with 0. So c of f of 1 of 0 equals 0 squared plus 1 equals 1. And then this number is used here. F of 1 of 1 equals 1 squared plus 1, which equals 2, and then repeats again. F of 1 of 2 equals 2 squared plus 1 equals 5. So it can easily be seen that this approaches infinity. However, if we were to look at to another c, for example, c equals -1, we can show that f of -1 of 0 equals -1 squared equals 0 squared minus 1, which is equal to -1. And then we put -1 back here. And we can say -1 squared minus 1 is actually equal to 0. But we know what 0 equals, and it's -1. So this is an example that would satisfy the Mandlebrot set because it just bounces back and forth. The areas here outlined, the areas here are the values that the imaginary values that bounce back, and the areas here are the imaginary values that approach infinity. So what's interesting are the values here on the border. These show the values that are slight variations of constant c's, so slight variations of imaginary numbers a plus b out. They're random patterns that are self-similar to infinity. So the different color shadings represents the varying amounts of time it takes for the c to approach infinity or to grow. And those are complex fractals. Here are some other examples of varying c values, imaginary numbers. For example, the value of 0.2 plus 0.5i, which is found right here on the Mandlebrot set, has this shape of Juliet set, which is a different... Okay, so I did a bad job of explaining what a Juliet set was. So basically, the Mandlebrot set applies to all c's in a recursive function. However, the Juliet set only applies to a specific c and analyzes its behavior on that function. So if you were to select a c within the black portion of the Mandlebrot set, you would get a Juliet set that would look like a cohesive circle, or a shape like this, or like bunny ears, in a circle in a cohesive shape. However, if you were to choose a c that was outside of the Mandlebrot set in the blue area, because the limit approaches infinity, you would just get dots kind of in different areas, and that basically is one dividing characteristic between the numbers that approach infinity and the numbers that stay small. Okay, that's good.